Yes. So here, nucleic acid. Few slide I will go a little faster. Where I need to explain that place, I will explain in more details, because here some of those like very basic like thing, those are elementary chemistry. Because of before your in your chemistry class, class 2 level, or even during the first year level, even you read in your organic chemistry some of those things. So nucleic acid, mostly two types of nucleic acid present in our body, in our cell. One is called RNA, that is ribonucleic acid, and the other one is DNA, deoxyribonucleic acid. Okay, so now I'm sure that same person, all of you know this, that ribonucleic acid and deoxyribonucleic acid. And here I should mention like the basic concept of DNA and RNA and how it works. But later on we will discuss in more details. This scheme is called flow of genetic information. The flow of genetic information, the central dogma of molecular biology. So the flow of genetic information is the central dogma of molecular biology. Dogma means the central belief, like which cannot be wrong. It's kind of very much true. It's kind of, like just need to be occur all the time. So this is central dogma. So here you can see that DNA goes to DNA, that is called replication. Then DNA goes to RNA, that is called transcription, and RNA goes to protein, that is called translation. Then why it's required? I told you that the information present in DNA, already you know that DNA is our genetic material. Now that information need to be processed into RNA, and RNA finally help to make protein, and this is the functional molecule. Protein is functional molecule. DNA is strictly, I would say, strictly, please mute yourself, some student, please. So strictly informational, that means the information is present here in DNA, and RNA is operational, right? So RNA help in this operation so that protein can be generated. And these are the process replication. Why replication is important? Say, for example, all of us, we started from single cell. Like now I told you that we have 10 to the power 13 cell approximately, but all of us, we started from a single cell, that is called zygote after fertilization, right? So now if you have single cell that contains some information, that is DNA, in order to make two cells in the next round of division, what you need to do? First, you have to replicate your information. The cell without information doesn't make sense. You have to have information, exactly same amount of proper information. So as a result of that, whenever your cell is getting divided, then before that, you have to replicate your information. That is called replication of DNA. Okay, sometimes I say duplication, that you are making that double information, and then you have to properly separate that information in two cells. This is also true for bacteria. One bacteria, although bacteria is not multicellular organism, but if you have one bacteria, that bacteria will divide into two. Before this division, that information should get into double, and then they should go, the equal amount of information should go into two bacteria in the next generation. So you need to always replicate your DNA during cell division, right? So here that is called replication, and then transcription and translation I will discuss in more details in other classes. Here DNA, you can see polymer of, what is DNA? Polymer of what? Can you tell me?
Nucleotides.
Amino acids?
No, polymer of nucleotides. DNA is polymer of nucleotides. And then this is double stranded. DNA is mostly double stranded, some exceptions there, I will tell you later. RNA is single-stranded, again polymer of nucleotides. Okay, so this is transcription. Based on this DNA, you make some transcript, and that contains single-stranded DNA. Nucleic acid polymer, and they have almost like the basic chemistry is same. It has little difference, like in sugar. I will tell you later, and then finally you will get protein. Protein is polymer of amino acid. Okay, so here also these three terms, if you don't know replication, transcription, and translation, you will never forget. I told
Sir,
you, yeah,
so RNA is a polymer of what?
polymer of nucleotides. RNA is also polymer of nucleotides, but there is some difference in sugar. I will come into that little later. Okay, so
Excuse me, sir.
yeah,
Sir, can you make the screen full screen there? It is not
uh,
visible. That is written polymer of.
Sir, both RNA and DNA are polymers of nucleic acids.
yeah. So 1 minute. So I will send you this slide. No problem. Okay, just now listen. So DNA and RNA both are polymer of nucleotides, right? Both are nucleic acid, deoxyribonucleic acid and ribonucleic acid. Just after 2-3 slides, it will be clear to you. But replication is means replica. You are making just one thing out of it, another thing, but those two things should be exactly similar. That is called replica. So that's why this is replication. When you are making DNA out of DNA, as I told you before cell division, it is absolutely required. Transcription, it's kind of transcript, right? You have like little bit defined information, but the basic chemistry is same here, polymer of nucleotides. And the translation, this term is called translation from polymer of nucleotides to polymer of amino acid. Why this is translation? Because I believe that if I give you the analogy, you will never forget. That, for example, you are in France, you don't know French language. So what you will do? You need a translator who can actually convert your language like into French and then the French language into another language like in English, for example. Both of you know, like so that way. So as a result of that, this is called translation because the language is completely different here. The RNA and DNA, they are polymer of nucleotides, but here polymer of amino acids. The chemical language is completely different. It's kind of nucleotides, it's amino acids, total different thing. That's why this step is called translation. Okay, so let me go through it, and then here nucleic acid. Nucleic acids are polymers, monomers are nucleotides, and then in the nucleotide you have like nitrogenous base, sugar, and phosphate. I will come into that. So here, if you see how nucleotides looks like, so you have one sugar, and that sugar is pentose. This is carbon 1, 2, 3, 4, and then CH2 here. Something I'm not writing here intentionally. So this is 5, but not 5. We denote it 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. You know why? Why this 1 prime, 2 prime? Because you have another big group here that is called nitrogenous base. You have a lot of carbon there also. So there we number carbon 1, 2, 3, 4. Here 1 prime, 2 prime, 3 prime. Later on you will see the structure, and here you have phosphate group. All together that forms one nucleotide. This is nucleotide. Okay, and so in nucleotide, what you have? In nucleotide you have sugar, you have phosphate, and you have nitrogenous base. So just one nitrogenous base, but we have total 4 different types of nitrogenous base in DNA. So that those nitrogenous base are called ATGC. Whatever you normally say ATGC, that is adenine, thymine, guanosine, and cytosine. Those are the nitrogenous base. This sugar part and phosphate part is common, right? So this is called nucleotide, right? So the nucleotide is the monomeric unit of DNA, right? Even for RNA also. So in DNA and RNA, there is some difference in sugar. I will discuss little later. But Nucleotides are the monomeric unit of nucleic acid. Nucleic acid is polymer and nucleotide is monomer. Remember that. Nucleoside, little smaller. So you have only the nitrogenous base and the sugar. These two things together, that means the sugar and the nitrogenous base, that makes this nucleoside. Whenever you add this phosphate with the nucleoside, that get nucleotide. So this is the monomeric subunit of nucleic acid. So all of this thing will be clear. Whenever I will send you the slide, you can just go through it today one more time. So now, what is the difference between RNA and DNA? As I told you, that the major difference actually comes from sugar. That is the most important thing. Here you can see that this is the sugar, pentose sugar, like 5 carbon sugar, right? Pentose sugar, 1 prime, 2 prime, 3 prime, 4 prime, and 5 prime. And here you have phosphate group here, right? So now, in the 2 prime position, in case of ribose sugar, you have OH. This is ribose sugar, and this is present in RNA. That's why we say ribonucleic acid. In case of DNA, we say deoxyribonucleic acid. It is also ribonucleic acid, but deoxyribonucleic acid. So do you know what's the difference of the sugar in DNA? Can you tell quickly from this figure? I didn't tell
That
you.
right,
Two dash position there is hydrogen
Yeah, very
instead of
good.
OH.
In
at
the 2
two dash
prime
position there
position,
won't be OH. It
At
will
the
be
two dash position there would be just H or
excellent.
OH.
Yeah. Now, yeah, please now mute yourself. You are absolutely right. In the 2 prime position, it will be H in case of DNA, not OH. But that makes, I would say, huge difference. This OH is very important. It is providing a lot of different properties. When I ask my students that what is the difference between DNA, RNA, many students, like now we take only MCQ exam because of this online teaching system, right? There are many other problems there. So in a normal semester, we take descriptive exam also, like more than 60% questions are descriptive. So there sometime I ask that what is the difference between DNA and RNA? Some student they write DNA is double stranded, RNA is single stranded. Yes, that is a difference. But I would say that is not the major difference. That is not giving you the property of RNA. Rather, the major difference is the presence of 2 prime OH in case of RNA in the sugar, and in the 2 prime position you have just H in case of DNA. That is the major difference, and that actually causes lot of different that provides lot of different properties. I will discuss some of those things. And another difference, sometimes students they tell that in case of DNA you have ATGC, and in case of RNA you have AUGC. Instead of thymine you have uracil. In your class 9 and 10 you have read this. I am sure that you can remember that AUGC. I would again tell you that T and U, that is not that much of difference. For all purpose, I would say for different properties of RNA that rely on the presence of 2 prime OH group in the sugar. Okay, so remember that, and I will explain that also why it is important. So here I told you that we have two types of nitrogenous bases. One is called pyrimidine, okay, and the other one is called purine. So these structures you don't need to remember. Just while you are going through it, how it forms hydrogen bonding and all those things are mentioned in the slide properly. For your understanding purpose, it's fine. You just go through it, but you don't need to remember this structure. I will not ask you in exam that draw this structure or what is this, nothing like that. But you need to know to understand how actually DNA double helix they held together, how they work. But you don't need to remember this thing. So now, in case of purine, we have two types of nitrogenous base. This is A and this is G. So those are purine. Those are a little bit bigger. Like you can see their molecular weight is much bigger than much more than like pyrimidine. Pyrimidine you have cytosine This is called C. And in case of DNA, you have T. In case of RNA, you have U. That's all. But again, I'm telling you, you don't need to remember all this structure, but in some slide, in order to understand the chemical and physical properties, you need to appreciate their structure, but you don't need to remember their structure. Okay. Now, here I already introduced that nucleotide means nucleoside plus phosphate. Nucleoside means sugar and base. You can see here, this is actually nucleotide because you have phosphate, you have nitrogenous base, and you have sugar. This is nucleotide. And the sugar part and the phosphate part is common in all these four. But this one is adenosine. That's why this is deoxyadenosine, or this is A. And this is here guanosine. This is G. Only this part is different. See, here you see the difference. So that way you have A, G, T, C. Those are like, I've just taken it from very standard textbook, just copy pasted here. So these four nucleotides are present in DNA, and they are the monomeric units of DNA. Similarly, in case of RNA, see, it was DNA here in the previous slide here. That's why you have H, you have H, you have H. This is 2' position. You have H here. But similarly, everything is same, but in case of ribonucleotide, this is ribonucleotide. You have
So you are
Sir,
muted.
you are
You are muted.
Not able.
sir, you muted.
So maybe some student did that either intentionally or non-intentionally, but so I'm just requesting all of you, please don't, mute myself because I'm not forcing you to attend the class, right? So
Sir,
if you
you can make us all attendees
yeah,
or
I know that, but intentionally I don't do that actually, but I can try, like do that also because normally people like students they don't do it. Again, I'm requesting you that I'm not forcing you to attend the class. If you are happy without attending class, and that is also fine with me, right? But whoever attending, whoever trying to understand, please let them understand. Let me discuss. Okay, so uh, that's all. So here, in this case, you will see, I just explained you the monomers of nucleic acid in case of DNA and RNA, right? Now let's see how this DNA and RNA, they can make the polymer, right? So here, something new we will see, that phosphodiester linkage. So again, if you go very slowly with me, not just see all those things. First, concentrate on this left-hand structure. This is DNA, just one strand of DNA. All of you know that DNA is double-stranded structure. Here we are showing just one strand. Like, so here you can see this is one nucleotide. That means here you have the sugar, here the purine base adenine, and here the phosphate. So this is one nucleotide. And in the 3' position you have OH, whether it is deoxyribonucleotide or ribonucleotide, whether it is monomeric unit of RNA or DNA, in 3' position you always have OH, and that OH actually helps to make the phosphodiester bond, phospho, P here, diester, one ester here, another ester here, phosphodiester linkage, so that the next nucleotide again can be attached. Again you have the 3' OH, again it can make phosphodiester bond. I am trying to explain almost every word also. Please try to understand. Phosphodiester bond, so that those nucleotides can be attached together and that will make some kind of thread, the polymer of nucleotides. And that way DNA and RNA are built together, right? Now, if you see RNA, the same thing, whatever I explained. Now you will see only the 2' position you have OH instead of H that is present in DNA. So I believe that all those things are clear. Only one thing it might give you some problem is that here it's written that 5' to 3' direction. This is very important. Don't ignore this. This is one of the most important thing. Without understanding this, this will give you trouble later. That 5' to 3' direction. What from where this 5' and 3' coming? This sugar number. See, if you consider this is DNA strand, forget about this RNA, this is DNA strand. So it can grow only in 3' direction this way. Why? Because you have this 3' OH is free. So another nucleotide can be attached here. Then again another nucleotide can be attached here. And the 5' here, see, in the 5' carbon here you have the phosphate. This is done. This way you cannot grow anymore. So that's why any nucleic acid, whether it is DNA or RNA, the chain can only grow from 5' to 3' direction. So here the 5' end just that is done with this phosphate group. Only the 3' end you have this OH group free here before addition of this nucleotide. So that OH can carry out some nucleophilic attack and that can cause this phosphodiester bond. I will come into that little later, most likely during the next.
Sir, can you please explain again the 5' to 3' necessary
Yeah,
quick?
yeah, sure, definitely. So this is one nucleotide. Okay, so this is one nucleotide, right? So if you didn't have this chain before, you had OH here because 3' should be OH always, right? But when it makes the chain, then H is gone and it makes this phosphodiester bond. So then if you number, this is 1', 2', 3', 4', 5'. So in the 5', this is already cell, the phosphate group is here. That way DNA cannot grow. The 3' OH is here. So this OH can carry out some nucleophilic attack and that can cause this phosphodiester bond formation. So as a result of that, this nucleotide has been added here. It attached. So again, you will have this OH here and that will carry out the same reaction in presence of some enzyme that we will be discussed in next class. So again, another residue will be, another nucleotide will be added. So again, it will be free here, OH. So 3' OH, that is carrying out the reaction. That is actually initiating the reaction. So in the 3' end, you can add another nucleotide. In the 3' end, you can add a nucleotide. So as a result of that, nucleic acid chain can grow from 5' to 3' direction, not in this direction. In 5' it cannot grow. Similarly, RNA, that everything same. It can grow only to 5' to 3' direction. Is it clear?
Yes, sir, but in RNA we also have OH on the 2' position. So why does that?
Yeah. Very good. Yeah, but why not 2', right? Why not 2'
Yes, sir.
is being extended? That is because of the property of enzyme that I will discuss in later class, in transcription class. Your question is very good actually, that why not? But the 3' OH can be actually used like during the process of this, like making this RNA. During that time I will discuss, but this is very pertinent and important question. Yes, that you
Okay,
can
sir.
say. Yeah. So now let me go to the next slide that I just told you DNA here. So and this is
Excuse me,
RNA.
sir.
Yeah.
Can you explain 5' to 3'? I didn't understand, sir.
So in 5' and 3', let me go through here again. So 1 minute. Just a minute. Yes. So can you see this pencil?
Yes, sir.
Yes, right. So in this pencil, so this is the sharp end. This is the sharp end here. Okay, and this is the blunt end. So if you think that this is the like polynucleotide chain, that means nucleotides are attached through phosphodiester bond, right? Here, at the beginning here, you have one nucleotide where the 5' carbon is attached with the phosphate, but it cannot carry out the nucleophilic attack. But here, whatever nucleotide present here, this serpent, just imagine that this serpent is nothing but 1,3' OH group. So that will carry out the reaction, that will carry out the nucleophilic attack in presence of some enzyme, which I'm going to discuss in next class. So as a result of that, another nucleotide will be attached here. So when another nucleotide will be attached here, then again you will get the serpent. That means the 3' OH is hanging here. So again, it will add another nucleotide. So as a result of that, the 5' end is capped with this phosphate. This is not growing, but the 3' since you have the free 3' hydroxyl group, OH group, it can grow. That's why DNA can grow, not DNA, any nucleic acid can grow only in 5' to 3' direction, not from 3' to 5' direction. Okay, so that is the idea. But I like, yeah, just let me go through it. I believe you will be more clear in couple of after two three slides. In some like some more structures are there, and then it will be more clear. Now, as I told you, in school days, you have learned that like the RNA is single stranded and DNA is double stranded like this. Okay, DNA is double stranded like this. So apart from that, one very important thing is RNA is less stable than DNA. That is very important, and that's why I would say that DNA is being used as a stable molecule, and DNA actually store our genetic information, right? But RNA is not stable, and RNA is operational molecule. RNA stay for short time in our body, in our cell, and then they get degraded, right? So that's why DNA store information. There are few exceptions in some viruses, but I will discuss that at suitable time. But DNA is our genetic material. If you see, in case of RNA, since you have the 2' OH also, in little alkaline condition, say for example, in our body, our pH, you know, what is the pH in our body, the cell, like the physiological pH, what's the pH? Can you remember? Or
Slightly greater than 7, I think, so 7.46.
yeah, 7.4, approximately 7.4. So little bit alkaline. So during that condition, what happened? This OH actually in little alkaline condition, it actually started, hydrolyzing this phosphodiester bond. So as a result of that, inherently RNA is less stable and RNA get degraded in our body. But I would say that is not anything problem. That is, I would say that is good for us. Okay, RNA should be less stable. Again, like all those classes are linked together. Okay, I'm telling you some points, some question. You will get the answer in the next class, maybe the class after the next class. So RNA is unstable, but that is good for us. Okay, that will actually help for our physiological function. But right now, here just try to understand why RNA is unstable, why it gets quickly degraded, and later on you will understand what is its benefit. So now, if you see that RNA is much more unstable compared to DNA, or you can say DNA is more stable, right? Now we will go into a little bit details of DNA structure. So I believe if I ask you who discovered DNA structure, I believe that all of you know, like you can actually tell that who discovered DNA structure. Watson and Crick, they actually proposed the DNA structure based on some experimental results, right? So here you can see how DNA looks like. So this is the model, and James Watson and Francis Crick, they published paper in 1953 in Nature paper, and they awarded Nobel Prize for the discovery of DNA structure. And this is based on some X-ray diffraction pattern, right? So X-ray diffraction is some kind of physical technique. So, in presence of X-ray beam, if you put some crystal, right, or, then in presence of X-ray beam, because of the electron like present in those crystal, they will diffract the X-ray beam, and you will get some kind of electron density map. And then based, like after analyzing that, you can actually like figure out what is the structure. So in our lab, we do this kind of work, but this is, I would say, scope of our, like, we cannot discuss this in this preliminary class, how we can achieve this thing. Or look, some of the students who are in physics department, I'm sure that at some point of time throughout your course, you will actually study this X-ray diffraction and crystallography to some extent, and even for chemistry student. For other engineering student, I'm not aware, but all the course details. But the thing is, from the X-ray diffraction pattern, Francis Crick and James Watson, they proposed DNA structure, and let's see how it looks like. Okay, so here some of the information is present here. I'm not going into it, right? So you can just go through it, and whatever, I will actually explain all of those things, but you can just go through it. That's charge of rule and all those things. So the thing is here, while I'm going through this, I'm discussing this slide that will cover whatever written in the previous two slides. Okay. So here you can find that DNA is double stranded, right? So you can see that 5 prime here, the 5 prime end of this sugar, and here see, this is the sugar, cytosine, not sugar. This is sugar, this is phosphate, this is the nitrogenous base. Again, phosphate, sugar, nitrogenous base. That way the chain is growing 5 prime to 3 prime end. And here 3 prime to, like here you have 5 prime here, 5 prime to 3 prime. Now, how how these two strands are present in DNA? They are anti-parallel. So this concept is little complicated. Let me explain this. The two strands in DNA, they are anti-parallel. So as I told you, if this is one strand, right? This is the 5 prime, this is the 3 prime end of your DNA, one strand. The other strand cannot be here. For other chemical and physical properties and packing of DNA, it should be like this. And that has some other benefit I will tell you later. So see, these two directions are different, right? Here in this strand, the 3 prime free end is here, right? So that way DNA is present. DNA's two strands are anti-parallel. One strand is going in this direction, and the other strand is going in that direction, anti-parallel. You have 5 prime, 3 prime, in this case 5 prime and 3 prime. That's why they are anti-parallel. And now those two strands are close by, and then they make some kind of helix. I cannot make an helix using this pencil, right? But they can form some kind of helix. But first tell me why those two things, two chains can be together. Do you know why they can stay together?
Hydrogen bonding, sir.
Very good.
The hydrogen bonding.
Yeah, very good. Hydrogen bonding. So let me come back there. Yes, here. See here that the hydrogen bonding between the nitrogenous base, that means those ATGC, whatever I told you, specific hydrogen bonding, I must tell that, specific hydrogen bonding. Now, this hydrogen bonding you will understand better if you know this structure. But as I told you, so Satyam, are you asking something to me? Okay, so it's fine. Now, you will understand better this hydrogen bond if you know the structure, but without that also just, if you can go without remembering this thing. So here you have to remember one thing, that adenosine always base pair with T, and you have just 2 hydrogen bonds in between them. And G that make hydrogen bonding with C, guanine and cytosine, they have 3 hydrogen bonding in between them, right? AT and GC, and this is called charge-up rule, that in double-stranded DNA, if you have adenosine 20% like here, so you should have 20% thymine also, because adenine and thymine, they form this kind of base pairing. And similarly, G and C, they are base pairing with each other, right? So that way DNA is formed. And here the antiparallel thing is again, I just included one figure. So when you will go through it, it will be little easier for you to understand and appreciate the thing. And now what Watson and Crick model for DNA structure is something like this. DNA looks like double-stranded and double helical structure. See, double helix, right? Those two strands are going like this. And now you have some kind of dimension here. So if it is an helix, so it is going like this. And now while it is going like this, to complete the full turn here, like total 360-degree, the distance is 36 angstrom here, from here to complete the one complete turn like 360-degree. And in between two nucleotides, you have 3.4 angstrom distance, right? So as a result of that, approximately 10 nucleotide pair present in this one turn. There are a lot of information. I know that this is right now difficult for you to remember, but when you will go through it, you will understand properly. But before that, let me explain how this double helix form. I told you that DNA is double-stranded, double helix. What kind of helix? Right-handed helix. How you can imagine right-handed helix? So make your thumbs up, like something like this. The right hand, not the left hand, right hand. So this finger, like this is your imaginary axis, and these two finger, like so these two finger, those two are two strand of DNA. And now your nail, the direction of nail, this is the direction. So if it's going like this in your right hand, this should be the right-handed helix. That's why right-handed. Left-handed, see, in opposite direction is going. So this is left-handed helix. But DNA is right-handed helix. So this is imaginary axis, nothing like axis present in DNA. Those two strands, they are going like this through this imaginary axis. But the screw sense is right-handed, right? That's why I'm showing in right-handed helix. And now while they are like going like this, when they finish like a complete turn, that is 360-degree, they accommodate around 10.4 nucleotides pair. Because why I'm telling you pair, because two strands are going together. That means two nucleotides, they are actually making hydrogen bond. So that you can appreciate here in this slide. Okay, so here, and in this case you can see this is just a ball and stick model, and this is a space fill model. This blue thing you can see, this is the backbone, that phosphodiester backbone. That means phosphate and sugar, and this white thing, those are the like coming from the nitrogenous base. So as a result of that, remember that those phosphodiester backbone, they are facing outward, but mostly the nitrogenous base, they are stacking together. Like nitrogenous base from two different strands, they are making hydrogen bond, like they are making hydrogen bond. In addition to that, they are stacking together. So I don't have the model right now when I take the class in actual class. So I have very big DNA model. I normally used to show this model to all students. So now the thing is, if you properly see DNA structure, in the next class I will install some I would say software, so that I can see the I can explain you the three-dimensional structure of DNA. But what I want to say, that the phosphodiester backbone, when it's going like that, that faces outward, and the nitrogenous base, they are staying a little bit inside and forming hydrogen bond. Do you know why? Why it is happening? I didn't tell you. If you can tell the answer, it is good, but if you cannot, that is also fine. See.
Can you please repeat the question?
Yeah, so when this double helix is going on in case of DNA, the sugar phosphate backbone, like if you see here in this slide, so this blue color thing is sugar phosphate backbone, like sugar phosphate, and from the sugar, the nitrogenous base is coming away, right? So in the structure you can see here, see, from the sugar, the nitrogenous base is coming out. So what I'm telling you, in the DNA structure itself, the sugars are nitrogenous base are little bit present inside the core in three-dimensional space. It is little bit difficult for you to appreciate because we are not showing three-dimensional structure, but sugar phosphate, they are staying little away. And I'm asking, do you have any answer of why it is happening? Because sugar and phosphate both are hydrophilic. They love water. Like phosphate group sugar, they are largely soluble in water. But now if you see the structure of nitrogenous base, they are quite hydrophobic. So they want to stay stack. Like if you have hydrophobic surface, you stack another nucleotide, another nucleotide. So there's some kind of stacking. So that way they can stay, they can be more stable in case of DNA, because like double helix, so that those nitrogenous base, they can stack with each other, and that precludes some water. So some water molecules cannot come very close by, right? Like definitely water molecules are there, but not too much. So as a result of that, this is some kind of packing. So whatever I told you, that not only, I would say, not only hydrogen bond, this hydrophobic interaction or this hydrophobic nature of this nitrogenous base, that also helps this DNA to stay in double helical structure. So in addition to that, I would like to ask you one thing. So the phosphodiester backbone here, you can see this is phosphodiester backbone. So what will be the net charge of phosphodiester backbone? Tell me. What will be the net charge of phosphodiester backbone?
Negative.
Negative charge, very much negative, because in every repeating unit you have one phosphate group. So then how did you expect that those two, like DNA chain, they are very close by and they are making some kind of helix? There should be some kind of repulsion. How did you, address this thing? The DNA is double stranded and that is stable, right? This is very simple question. You don't need to know biology to answer this. So what can you think about this? How it can be, you can overcome this problem? Because two strands, both are negatively charged. They are coming each other close. Then they
So
can repel each other. Huh?
maybe nitrogenous bases are positively charged.
Nitrogenous bases, they are not contributing, I would say that way. Mostly they are involved in hydrogen bonding. Actually, you know what happened in our body, like DNA is present in living system. So in our cell, you have lot of, mostly like sodium, potassium, those ions, they are constantly interacting with this phosphate group. And they always try to neutralize this phosphate group so that those two strands are close by. Okay. And here I would like to tell you, like there is one very good experiment you can do in lab, actually, like like very like in our lab also you can do, and that is very cost effective experiment. You don't need to spend a lot of money. The experiment is that if you take like 2 glasses of water, like I have just 1 glass, another glass, one is completely deionized water, completely deionized, remember, no more ion there. And the other one is kind of normal water, tap water, right? So please mute yourself. Some student, they are uh, unmuted, so please mute yourself. So now this water is completely deionized, and the another glass in my left hand, if it is normal water, and if you put same amount of DNA in those 2 glasses, you will see the DNA, double-stranded DNA present in this completely deionized water, slowly they will be converted into single-stranded DNA, right? And that you can record also. That there are some very simple experiment that you can record. Okay, that DNA is getting single stranded. You know why this DNA is getting single stranded here? I told you. Tell me why.
Repulsion.
Yeah,
Due to
because
repulsion.
because I told you that completely deionized water. So whatever, some charge like some sodium, potassium, those are attached to the DNA like phosphate. Over the time they will come out in the solution. So as a result of that, those two strands will slowly like repel each other, and that will help double-stranded DNA to make single-stranded. Okay, so that is one technique. So you can make double-stranded to single-stranded in an artificial condition, whatever I told in deionized water. The another very simple thing is if you have double-stranded DNA here, like in this tube, just consider that this is not a glass. This is just small tube. You have double-stranded DNA, right? If you hit this DNA, this solution, then what will happen? If you hit this, then you are providing some energy, and that will break the hydrogen bonding between A, T, G, C, all those hydrogen bonding, and that will also like make those double-stranded DNA into single strand. That is called denaturation. Denaturation of DNA. I have just 2 slides left. Let me explain and then I will leave. Okay. So the basic principle I already told, but let me go through the slide and then today's class will be done. I hope that you don't have class at 10, right? As I asked you before. So that's why I'm extending like 5-10 minutes more, and then I'll be done. Here. So here, whatever I told you right now, so this is double helix DNA. You can. So now, if you like, increase the temperature, like for example, increase that this DNA is present in solution and you are increasing the temperature of this DNA. So you have one tube, like some solution, you have a lot of double-stranded DNA, you have a lot of double-stranded DNA. So now, if you increase the temperature, then what will happen? The double strand will slowly get single stranded because those hydrogen bond between A, T and G, C, that will be, that will destabilize and that will be broken. So as a result of that, you will get the single strand. This process is called denaturation. If you increase even more the temperature, then the 2 strands will be completely separated, like strands are separated. But this is a reversible process. So you just, you are increasing the temperature, you were increasing. That's why it's happened. Now, in this tube, this temperature, again, like, cool down slowly. You have to make it slow, definitely. But then, again, you will get double-stranded DNA. This is called annealing. So these 2 terms, try to remember, denaturation and annealing. Annealing means, again, those 2 strands of DNA, they are falling like together. That means they are forming proper adenosine, thymine, cytosine bond. Okay. So now, I would tell you one experiment. This is the last slide. So if you have one slide here, sorry, one tube here, tube A, and here tube B. And both these tube, you have equal amount of DNA. Amount, I'm telling, equal amount of DNA in terms of microgram, milligram, or length, like equal amount of DNA. And now, what you are doing, you are increasing the temperature of this tube, both the tube. And then you are plotting that result in this curve. So here in this x-axis, you have the temperature in degree centigrade, and the y-axis is denaturation. Denaturation means, right? The separation of strands. How you will measure that? I didn't mention that. So we measured that from the absorbance at 280 nanometer wavelength of DNA. So I would like to tell you that DNA absorbs maximum at 280 nanometer wavelength of light. Why? Because of that property of nitrogenous base. Now, when you have double-stranded DNA like this, I told you that nitrogenous base, they are staying a little bit inside. So whenever they are making single strand, then their absorbance at 280 increase, right? So as a result of that, when DNA gets single stranded, they absorb more at 280 nanometer wavelength of light. So that is here in the y-axis. Actually, you are plotting a 280 value, the absorbance at 280 nanometer wavelength from these 2 tubes, and that is like proportional to denaturation, because more denaturation means more A280 absorbance, because DNA is getting single stranded and those nitrogenous bases, they are facing more and more this wavelength of light and they are absorbing more. So now when you carry out this experiment, like you are decreasing the temperature, what you observe that if I tell you that this is A and this is B, that means the result of this the blue curve you can see that is coming from tube A, and the result coming from tube B is this like brown curve, right? Now tell me what is the difference between this A and B in terms of DNA or nucleic acid composition? Can you quickly say what's the difference between A and B?
A
So B
denatures
is
quickly.
DNA.
Just one by one. So Probal,
So B is DNA.
both are DNA. I told you both are DNA and both are same length of DNA. Someone else?
Sir, in A it is denaturing quickly. Like,
Yeah, quickly, but why?
at lower temperature.
Subhadra, why?
Sir, I think in B more hydrogen bond.
Very good, very close. Then something add someone like some other student, then it will be completed. All of you like quickly, you just went step by step. Yeah, you are right. More hydrogen bond. That's why it needs more temperature. Because I told you the same length of DNA, same amount of DNA. But the thing is that in this case, if you see, all of you are right, like to some extent, like no, provide little answer. So in these two tube, in case of tube B, you have DNA that contain more GC rich sequence. Here you have more AT rich sequence. In A and T, you have two hydrogen bond. In G and C, you have like more. I would say three hydrogen bond. So as a result of that, if I ask you that what are the like difference between this A and B tube in terms of nucleotides composition, I didn't ask you like very clearly, intentionally, just to like get your answer what you were thinking. So in terms of nucleotide composition, in case of B tube, you have more GC rich sequence, you have more GC. That's why you need to break more and more hydrogen bond. You need more temperature here. So here you can see the curve is growing up. Why? At this temperature, the DNA they are getting separated now, and as a result of that, the denaturation is increasing. That means A280 value is increasing, and at this point, it's not increasing anymore. Why? Because all those double-stranded DNA now they are in single-stranded form. So whatever temperature you increase, that will not help you. That will not increase A280 value anymore. This physical properties is absolutely important. This is very important for your next class also. For different purpose, you have to understand this thing. So as a result of that, some students left, but whoever present here, please don't forget this thing. This is very important for many other applications, that some other application where we use DNA for different experiment. You need to know this property, that when you are warming or increasing the temperature, that breaks hydrogen bond, DNA double strand can make into single strand, right? If you have more G series sequence, you need more temperature. That's all. Today's class is done. I will ask you just one small question, then you will leave. So this is, a small but interesting question. So here, I'm telling you that you discover some unknown organism, say for example, some unknown virus, okay, and then you have all the facility, you are working in some lab so that you can analyze nucleic acid, right? Analyze the nucleic acid of that organism, of virus, whatever you tell. Whatever I told you about DNA, that A base pair with T and G base pair with C. So as a result of that, in double stranded DNA, so A by T should be 1, right? As well as G by C should be 1, because G always base pair as C. But whatever new virus you have discovered, after analysis of DNA, you found that A by T not equal to 1 and G by C not equal to 1. Can you comment the property of nucleic acid present on that organism? This is very like
RNA,
Huh?
The DNA is not uniformly like helical. Means at some places it is close and at some places it is like far.
Yeah, but you are going in right direction. But how that can happen? I told right, DNA is double stranded helix. That's why.
So here it will be single stranded like that.
Yeah,
Sir, one strand is long and one strand is short.
exactly. That can happen. Theoretically, your answer is right. Whoever telling right, that is right. But I would tell you the actual like whatever you told that one strand is short, right? Theoretically, that is right, but biologically, that is
So
not.
this is true for all
So
viruses or
maybe
only some viruses?
No. Only like whatever the organism you discovered there, you found this. So I just some like some like I would say hypothetical question I would say, but this is true
maybe
for
this
some
can
organisms.
also happen that
Yeah, yeah,
there are
yeah. I'm giving you the
simultaneous
answer.
bonding.
Yeah, you are like most of you are right. I'm giving you the answer. Actually, what happened? Many viruses they have single-stranded DNA as their genetic material. So the answer will be the DNA we are talking about here, single strand. I told you this part here. This is just to explain that why A by T equal to 1 and G by C equal to 1 because DNA is double-stranded, right? But some viruses they have single-stranded DNA. And as a result of that, if that is single stranded DNA, then there is no question of double strand formation. So as a result of that, A by T not equal to 1, G by C not equal to 1. Sometime if I say that they have like A, U, G, C as their composition in their genome. Now A by U equal to 1 as well as G by C equal to 1 in that organism. Then what you can comment from this nucleic acid analysis? I would say this virus contain RNA as their genetic material. Why? It has U instead of T. And not only RNA, they have double-stranded RNA. Why? See, A by U equal to 1. That means G by C equal to 1. That means they have double-stranded RNA. Yes, this is possible. Some virus, they have double-stranded RNA. Whatever I told in terms of conception, you don't need to remember any of this virus name or any of those things. But just think if you face this kind of like analytical question so that you can address properly. Okay, so that's done today's class.
Uh, sir, how will we study for the test? Means questions would be from how type, which type?
I would say whatever I discuss in the class, if you can get all those things and whatever written in the slide, it will address 100%. But remember, the way I tried to discuss, I didn't tell you a lot of terminology, lot of those things. Mostly I tried to like explain you some of those things. Your question will be something like that. Like even after the exam, whatever feedback I get from my student like previous semester, most of them, like almost all of them, they are happy about the question paper. You will get very much analytical question, something you have to think and you have to provide answer. And in order to answer, pay attention in the class, that will be fine. So whoever asked this question, I would like to tell you, by tonight, you will get this slide, right? Whatever I discussed, and one like practice question paper also, right? So you can, like while you are solving that question paper, so you have to go through the slide so that, at least one time you will go through the slide and that will be good enough. And after all, I am here. So if you have any additional question, just write me one email. Uh, you will get I will send you all of you another email with my email ID and everything. So you can send me email and, any problem, anything you can ask me. Okay, is it clear?
Hello, sir.
Yes, Prabal.
Sir, I have a doubt.
Yes.
Sir, what was the answer of that question where you asked that sugar and phosphate chains are negatively charged, but still the DNA is held tightly? So why don't they get separated?
So I was telling you that DNA, if you think that every alternating unit, they have like this negative phosphate group, those are negatively charged. Okay. And DNA is double stranded, right? Double stranded, they are close by. So this phosphate group, negatively charged two strand, they will not be very happy to stay very close by. So what happened in real life in physiological condition, these phosphate are always interacting with like positively charged ion like sodium, potassium present in our body. Now I was trying to explain something that instead of heat, even in a tube, if you put double-stranded DNA little bit, and if the water is completely deionized, not at all ion there, and that shake it for like few minutes and wait for some time, then you will slowly see that double-stranded DNA, they are getting separated because those ions which are bound to phosphate group, they are like positive ion, they are also coming into the solution. As a result of that, the DNA double strand will be unstable and it will make single strand. Is it clear, Prabal?
Yes, sir. Thank you.
Okay, thank you very much. So please, you can leave now because you have to prepare for the next class. And I told you like some of the thing that if you have any query, you just email me. Thank you very much.
Thank you, sir.
Yes, thanks.
Thank you, sir.
Yeah.
Thank you.
Thank you, sir.
Okay, thank you. I will send you material and you can just go through it. Thanks.